Alright, hello class. For this video, it's just going to be part 2 of our trig substitution stuff. So we did do a lot in that first part. There's a lot to trig substitution. This video, I just wanted to go over some more examples, maybe some more complicated examples, because these things can get pretty nasty. So let's just take a look at a couple more examples. And just to give ourselves a little more experience looking at these, in case there's some really tough ones that pop up in the homework. All right, so here we have the integral of 9x squared minus 25 all over x cubed dx. All right, and here we are given the condition that x is greater than 5/3. That's mainly just so this thing under here is always positive. Okay, so when I look at this, I think that, okay, we have, this should be a secant pattern, right? Because we essentially have our x squared minus our a squared. The only problem is we don't just have the x squared. Okay, when we have this, we somewhat like this in the last video. There are a lot of ways you can go about doing it. If I take this and say factor out the 9, you'll get x squared minus 25 over 9. So what we can do is just set this transformation up as x equals our a secant, but we're going to use this as our a squared, this 25 over 9. So if 25 over 9 is our a squared, then our a is 5/3. You'll notice that matches with what we have here, essentially. But there are other ways you can deal with this, but in either case, you're going to end up with x is equal to 5/3 secant theta, okay, which makes dx equal to 5/3 secant theta tangent theta, d theta. Okay. Now we have a few things to replace here because I have some extra x's in here. I don't think we've seen an example like this before where I have some extra stuff. So our x squared goes here like usual, so our x squared is going to be the 25/9 secant squared theta. Okay, but we also have this x cubed here. So x cubed, well, we're going to cube this. So it'll be 5/3 cubed, so that's 125 over 27 secant cubed theta. Okay, so now we've got our new integral we can set up. So let's do that. We'll have 9, and then the x squared gets put in as this 25/9 times secant squared theta, okay, minus 25. And more than likely, well, not more than likely, sorry. I'm putting the replacement parts in yellow here, or I guess that's orange. Okay. Then the x cubed, that becomes 125 over 27 times secant cubed theta. Now, I'm hopeful that some things will start canceling. And then when we get to the dx, well, dx becomes 5/3 secant theta tangent theta. So that's what our dx becomes, 5/3 secant theta tangent theta d theta. And it does. We do have a cancellation, right? This secant cancels with one of these down here. So we'll actually have a secant squared down there. Okay, so let's simplify this a little bit. Okay, the 9's here cancel. I should write that in too. So now we have the integral of 25 secant squared theta minus 25 underneath my square root. Here I have 125 over 27. So what I'm actually going to do, since we're dividing by this fraction, I'm going to invert and multiply it instead, just to get that out of our way. All right, so I'll leave the secant cubed down, or secant squared down there. But here, I'll rewrite this as 27 over 125, and that'll be times 5/3. So now it's hopefully easier to see that the 3 will cancel with the 27 and leave a 9, and the 5 will cancel with the 125 and leave a 25. Okay. Then here we're just left with a tan theta d theta. Okay. So let's simplify this a little more. Also here we're going to use our Pythagorean identity, and hopefully you've seen this enough times now to know that this just jumps to 25 tangent squared. And then that'll be secant squared theta, and then we'll have just 9/25 tangent theta. Okay, d theta. And then this will just simplify down to 5 tangent theta over secant squared theta, then times tangent theta d theta. I left off the 9/25, so let me sneak that in here. Nice thing about erasers. And we get another cancellation. This 5 will cancel with this and just leave a 5. Okay, so now we are down to just the integral. I'll bring the constants all the way out. 9/5 integral of, now we have tangent squared theta over secant squared theta d theta. All right, now here, there are quite a few ways we can tackle this integral. Okay, all of them are going to involve identities of some sort. Some of them, you know, well, there are just a lot of ways we could go about it. What I'm going to do is I'm just going to rewrite the secant squared in the denominator as cosine, because if we divide by secant squared, well, secant squared is 1 over cosine. Right, and if we invert and multiply, what we'll end up with is tan squared theta just times cosine squared theta. And this helps us because tan squared theta we can rewrite as sine squared theta over cosine squared theta. All right, so I chose this way of just rewriting these things so that stuff cancels. So those cosine squareds cancel for us, and now we just have an integral in terms of sine. Okay, so we have 9/5 integral of sine squared theta d theta. There are other ways you could go about it. There are other identities you could apply, but I tend to start with the ones that just sort of rewrite the function. Okay. Now we have an even power of sine, so we have to use our half angle. So let me write that down for you. It's going to be a half angle. So you see where these other methods are popping up in these new methods? Unfortunately, that's just the way it goes with these. Okay. So I should make that a theta. So when we do the half angle identity, we get a 1/2, and with the sine squared, it goes to 1 minus cosine. Okay, so then we get, if I move this, actually I'll go ahead and integrate, because that 1/2 isn't going to do much. So the 1/2 times the 9/5 will give us 9/10, and then the integral of this, well, I'm going to get theta minus, and here we'll get a 1/2. It'll be sine in this case, sine of 2 theta. Oops. Plus c. Okay? And in that first example we used, I'm going to want to use that identity, that sine of 2 theta is 2 sine theta cosine theta. Okay, it's a lot easier to deal with our reference triangle. So I'll just say that this is for the reference triangle. If we didn't have to do a reference triangle, we could just leave that like that. But trying to get a 2 theta on our reference triangle is kind of a pain. All right, so this 2 sine theta cosine theta will cancel with the 1/2. So we'll end up with just a 9/10 theta minus a 9/10 sine theta cosine theta. Okay, so this identity is also really, I almost said popular. It's probably not popular, but it's used a lot. It shows up a lot in these, and it can be really helpful in a lot of different situations. Okay, so now we need to set up a reference triangle because when we did this, notice our answer, we don't even see a secant, and that's what we started with. This was our transformation here. Okay. Now, let me rewrite our transformation here. We had that x was 5/3 secant theta. Okay, which we're going to move this over. So multiply by the reciprocal and get 3x over 5 is equal to secant theta. All right, now this tells us a few things. One, it tells us that if we take secant inverse of both sides, we'll get that secant inverse of 3x over 5 is equal to theta. So we can now replace this theta. So whenever you get just a theta all on its own, that becomes, in this case, a secant inverse 3x over 5. Okay? And then now we need the reference triangle to get these. So secant flips cosine, so it will be the hypotenuse over adjacent. So here's our right triangle. The hypotenuse is 3x. The side adjacent is 5, so that means the side opposite is going to be, when we square this, we'll get 9x squared minus 25, and I just want to make sure that that lines up with what we started with back here. Yes, 9x squared minus 25. Perfect. Okay. It's always a good thing to check, just to make sure you're rolling. Now, I will say we don't need to really do much work for cosine because cosine is just secant flipped over. So if secant is 3x over 5, then cosine is going to be 5 over 3x. Okay, that's just us flipping over our transformation. Sine, on the other hand, is opposite over hypotenuse. So it is going to be the square root of 9x squared minus 25 all over 5. Or, sorry, 3x, the hypotenuse. Okay, so let's put this in. Right, we'll get 9/10 times secant inverse of 3x over 5, okay, minus 9/10 times, this will be the square root of 9x squared minus 25 over 3x times 5 over 3x. Okay, well, notice that the 3x's, these come together to give us a 9x on the denominator, so the 3's will cancel with this 9 when they come together, and sorry, that will be x squared. Okay, so our final simplified answer, I should make sure I put my plus c's, we'll get 9/10 secant inverse 3x over 5. Okay, then I'm going to move this 5 out to say that this is going to be 5 times the square root of 9x squared minus 25 all over x squared plus c. Whew, and we're done. Okay. All right, let's look at another one. Okay, so looking at this example here, as given, this doesn't look like any pattern, right? I mean, this doesn't really strike me as anything. We could factor the numerator, okay? That we could definitely do. But this denominator here, I'm not seeing any pattern, okay? So it, just like before, there might be some work we have to do before we ever get down to a substitution. Okay, so here, this should factor into, the numerator should factor into an x minus 1 all squared, right? Because it's a perfect square. Okay. Unfortunately, this denominator won't. Okay, it won't factor. Because if we wanted to look at factors of 10, that would sum up to be -2. Your options are like 10 and 1, 2 and 5, and that's never going to happen. So it looks like we're going to have to go to our good friend completing the square. All right, so we're going to try to complete the square, and it's actually kind of nice because we already know what would be a perfect square, right? The perfect square for x squared minus 2x is the plus 1, okay? Since that will factor into x minus 1 all squared. So if we had a 1 right here instead of a 10, that would be great. So that's what we're actually going to do. I'm going to do this over here, so I'm not working with the square root and everything anymore. So x squared minus 2x plus 10. Well, we can complete the square by adding in a 1, but by also subtracting the 1. And we'll leave that plus 10 there. So it ends up giving us this thing factors like we want, okay, and then this becomes a plus 9. All right, so after completing the square, our integral, I'm also going to factor the top. Our integral is going to become x minus 1 all squared all over the square root of x minus 1 squared plus 9. Okay. Now we are in business, okay? Now I see the tan inverse pattern, right? This is a tan inverse pattern. Or not tan inverse, but just the tangent pattern. And you might think, well, hang on, that's an x minus 1. It's not just an x. But when we do the transformation, we can just do this, right? Instead of saying that x is equal to whatever, I'm going to say that x minus 1 is equal to, and here my a is 3, so it'll be 3 tan theta. Okay? So basically that x minus 1 is 3 tangent theta. Now there are other ways you could do this, but to me this is the nicest way to go because we just leave off that x minus 1, right, until we need it later. So that means when we differentiate this, the derivative of x will be dx, and then constant goes to 0, so we just get 3 secant squared theta d theta. All right, and so now not only does this mean that x minus 1 all squared becomes 9 tangent squared theta. We can put that here and here up top. All right, so our new integral becomes, well, the x minus 1 all squared becomes 9 tangent squared theta. Then underneath the square root, we get 9 tangent squared theta plus 9. Then our dx becomes 3 secant squared theta d theta. Okay. Then, like always, at this point, we do a Pythagorean identity. And again, you do this enough times, you know that what we get to is the square root of 9 secant squared theta. And whoops, then 3 secant squared theta d theta. So you'll notice that I'm not bringing these together yet. I'm just going to wait until the very end because things will probably cancel. And turns out some things definitely will, because we will get the integral of 9 tangent squared theta. The denominator will become 3 secant theta. And then here this 3 secant squared theta stays that way. Okay, and so the 3's cancel. This secant cancels with one of these secants. And so now our integral reduces down to 9 tangent squared theta times secant theta d theta. All right, now this is the case where our tangent exponent is even. Okay, so what we can do is so unfortunately, this isn't going to be one of those nice ones where we can just break a piece off, right? I can't break a secant squared off. I could break a secant theta, tangent theta off, but that wouldn't actually help us very much. Okay, so what I'm going to do is I'm actually going to do a Pythagorean identity again. Okay, so I'm going to get, so tangent squared theta is going to be secant squared theta minus 1 times secant theta d theta. And the reason I did this is because I can distribute this through and get that this is the integral of 9 secant cubed theta minus secant theta d theta. Okay, and we've done this one a couple of times now, the secant cubed and secant. So based on some of our previous work, in fact, I feel like I've done it enough times now to almost just know that the reduction formula for secant cubed is secant theta tangent theta over 2 plus 1/2 times the integral of secant theta d theta. So that's this piece, right, from our reduction formula. Okay. But then we also have this minus the integral of secant theta d theta here. Okay. Whoops. I see there. That should have been in parentheses. So should be more like this. Okay. Now the reason I did this is now I have a half of this integral minus that, so I could say that this is 9 times all this, secant theta tangent theta, over 2. A half minus a whole is minus a half. Okay. So maybe some people do have that reduction formula memorized. So this would be 9 secant theta tangent theta over 2 minus 9 halves natural log secant theta plus tangent theta plus c. Okay, so now we need to get this back into x's. So we want to go back to x's with a reference triangle. So to do that, let's go back up here and find our transformation. That was this guy right here. X minus 1 is equal to 3 tangent theta. Well, to make it a little more useful for a reference triangle, we're going to divide by 3. And we'll get x minus 1 over 3 is equal to tangent theta. So when we set up our reference triangle, okay, remember tangent is the side opposite over adjacent. So opposite will be x minus 1, adjacent will be 3. And when we use the Pythagorean theorem, we're going to get the hypotenuse is x minus 1 all squared plus 9, which is not exactly what we started with, but it's what we were able to here reduce down to. Okay, so we had to do a little bit of algebra before we were able to finalize that. So that's going to let us finish this off. So we already know what these tangents should become, but that's going to let us find the secants, right? Because from here, our secant, which secant theta is the hypotenuse over adjacent. So that will be the square root of x minus 1 squared plus 9 all over adjacent, which is 3. Notice that tangent is also over 3. We're going to use that here. Okay, so to simplify this, I'm going to put the 9 halves on the outside. So it'll be 9 halves times secant, which is the square root of x minus 1 squared plus 9 all over 3. Times our tangent, which is x minus 1 over 3. So these two 3's will cancel with that 9. That's nice. Then it'll be 9 halves natural log absolute value of this square root stuff over 3 plus the tangent, which is x minus 1 over 3, absolute value plus c. And we're going to do what we did in the last lecture, where we have the same denominator in the ln. What we can do is basically just drop all that and get this. It'll be 1/2 times the square root of x minus 1 squared plus 9 times x minus 1 minus, I messed that up, didn't I? That's 9 halves, not 9 thirds. Sorry about that. 9 halves natural log of the square root stuff plus x minus 1 plus c. Whew, and there we go. All right, so this up here, remember we just used that reduction formula. Again, that's not something I expect people to have memorized, but knowing it will definitely speed things up for you. All right, so let's find another funky example that we can cruise through. Okay, so for this example, we have the integral of 1 over x cubed times the square root of x squared minus 100. So this one, there's not much extra work to do to find our pattern. This is the secant pattern. Right, x squared minus a squared. So this tells me that a is 10. In fact, if you see this, usually that is kind of a dead giveaway that this is a secant pattern and that is our a. Right? I think if you look at all the examples we've done with the secant inverse, that's usually given to us like that. Okay, so our substitution, we're going to do x is equal to 10 secant theta. So then dx ends up being 10 secant theta tangent theta d theta. Okay, so here we have some extra stuff too. So the x squared becomes 100 secant squared theta. Okay, then x cubed is going to be 1,000 secant cubed theta. Okay, so we have more things to fill in, but this x squared becomes this x cubed becomes this, and the dx becomes the 10 secant theta tangent theta. So hopefully this simplifies into something that we can actually manage. You never know with integrals. Like with derivatives, derivatives you can always differentiate. I mean, there's always a rule. It's hardly ever I can give you something that you can't integrate, differentiate. But with integration, it's a whole other story. It's a completely different beast. There are plenty of things that can't be integrated. Anyway, so our x cubed, that becomes 1,000 secant cubed theta. Then we'll have the square root. Our x squared becomes 100 secant squared minus 100. So that part is fine. Then we have our dx, which is going to become 10 secant theta tangent theta. I'm actually going to just stick that in the numerator. All right, so I'll put 10 secant theta tangent theta d theta. So right off the bat, this 10 will cancel out one of those zeros there, and this secant will cancel one of those secants and just leave 2 of them. All right, then write some of this down. So we'll have 100 secant squared theta in the denominator. And then, remember, we still have to use the Pythagorean identity here. So I'll just say pi there. And hopefully by now, it's not a surprise that this becomes 100 tangent squared theta. All right, now, this simplifies. 100 tangent squared theta underneath a square root is going to be, let me rewrite some of this stuff. We still have the 100 secant squared in the denominator. This is going to end up being 10 tangent theta d theta. Okay, and so now the tangents cancel. So we have, when we simplify this out, have the integral of 1 over 1,000 secant squared theta d theta. And we'll tackle this like we did similarly when we had a secant squared in the denominator. That's just going to come out to be 1/1000th times the integral of cosine squared theta d theta. Okay, which here we use a half angle identity. All right, so With our half angle identity, I'll go ahead and move the 1/2 outside, so we get 1 over 2,000 times the integral of 1 plus cosine of 2 theta. And now we can integrate. All right, so let's do that here. We'll get 1 over 2,000 times theta plus 1/2 sine of 2 theta plus c. Okay. Oh boy. Okay. Now, the theta shouldn't be that hard to deal with. The sine of 2 theta, we're going to use that same identity again. So let me distribute this and say this is 1 over 2,000 theta plus 1 over 4,000. Actually, I don't need to do that because sine of 2 theta, that's going to become 2 sine theta cosine theta. All right, so the 2 there and the 2 there will cancel, so it'll just be 1 over 2,000 sine theta cosine theta. Okay, and so here's where we need to translate back. So let's go all the way back to our transformation. What was it? It's easy to kind of forget these things, get them confused. All right, so here we have x is equal to 10 secant theta. So I'm going to go ahead and skip a step when I rewrite this as x over 10 is equal to secant theta. So this tells me that secant inverse of x over 10 is theta. Okay, so I can replace theta with that. All right, then for the sine and cosine, well, cosine is just going to be this flipped over. And you might be able to guess what sine will be based on the patterns we've been dealing with, but we'll go ahead and set up the reference triangle. Secant is hypotenuse over adjacent. So that means the side opposite is going to be the square root of x squared minus 100. So yeah, sine theta is going to be the side opposite over the hypotenuse, which is x. Okay, so the more you do these, the more you start to see that there's these patterns that keep showing up, and we keep getting similar things as we do this. Okay, so our theta becomes secant inverse of x over 10, and then sine theta is our square root stuff, and the cosine is 10 over it. So I'll just write it like this, 10 over x. And I guess I did it out of order, but it doesn't matter that much. And now our final simplified version. I'm going to just factor this 1/2000th out. That looks kind of gross to me, writing it twice. Okay, so that we will get 10 times the square root of x squared minus 100 all over x squared plus c. Oh boy, and we are done with this one now. Alright, so one last thing I really want to show, other than, you know, we could get progressively more and more complicated, but at some point it hits a point of sort of diminishing returns on like how meaningful that is. But I wanted to show you, if you have definite integrals you often don't have to set up, you often don't have to transfer back to x's, right? Because you do some work here and to get things in terms of theta, and it often saves you a little headache, right? It may not seem like that would actually happen, but it will. So here, this is definitely a tan pattern. Okay, so we're going to let our x be, well, our a is 1, that's nice. So we're just going to have x be tangent theta, which makes dx equal to secant squared theta d theta. Okay, now, when we do this new integral, these limits are in terms of x, but when we move to thetas, okay, we need to now get our limits in terms of theta. Okay, so this should hopefully mean we don't have to create a reference triangle at the very end, but we may need to know a little bit more about our trig function. So here, when x is equal to 0 for this limit, so here's the x equals 0 limit, okay, what that basically means is we're looking at what we get when, or what angle would make tangent equal to 0. So tangent is equal to 0 when theta is equal to 0. So we're going to be using our values from the inverse functions when we do this. Okay, and then when x is equal to 1 over root 3, well, that is basically saying, oh, when does tangent equal 1 over root 3? Well, you could look at a unit circle or look at some other things, or you might just know that's pi over 6. Okay, so our new limits, our lower limit becomes, well, it just stays 0, but now our upper limit becomes pi over 6. Okay, and we have this new definite integral. And when we have a definite integral, we don't actually have to translate back to x's. What we can do is just evaluate it directly when we get the answer. Okay, so we need to do our Pythagorean identity. So we'll get down to the integral from 0 to pi over 6. This will now be the square root of secant squared theta, right, times secant squared theta d theta. And well, when we simplify this, this will come out to just be a secant, so we get secant cubed again. Okay, so using that reduction formula, we'll get secant theta tangent theta, okay, over 2. I think it's a plus 1/2 times the natural log of secant theta plus tangent theta.